Good evening. I'm Hyun-Bin. I'm PhD student at Amelia Postec. Today, I'm gonna present MMM Generative Mass Motion Model, which is presented at CVPR 2024. So, in this paper, it proposed a novel but simple motion generation paradigm, which not only generates the motion from text, but also has capabilities of editing the motions, such as upper body editing and motion in betweening and long sequence generation. So these innate motion editing capabilities are from the mask modeling in training stage, which enables simple motion editing by just placing mask tokens in the place for editing. So this mask motion model achieves high fidelity and faster motion generation performance on the text to motion text and also all the other editing text compared to the existing. 로그아웃 됐는데 어떻게 하죠? 로그아웃이 됐다는데 계속 해도 되나요? 네. So compared to the existing diffusion-based models and also compared to the auto-regressive models. So this is the overview of the model, and A and B are the training stage, and C is the inference stage. So MMM consists of two key components. First is the motion topology that converts the raw 3D human motion into discrete latent tokens. And second is the conditional masked motion transformer that predicts masked motion tokens based on the input conditional text tokens. So once training the VQVA and the transformer, they iteratively generate the motion tokens from the this mask tokens. And note that this is not an auto-regressive model. The model uses the parallel decoding strategy for generating the motion tokens. So they generate the motion tokens from the mask tokens, and they then again mask out the motion tokens and also generate the motion tokens from the mask tokens. And they decay the masking ratio given the iteration time. So they have two-stage training process. First, they train the motion tokenizer, which is, as you well know, just the VQVA, and they learn to encode the raw motion sequences into the sequences of discrete motion tokens. And this is the objective of vector quantization, which minimizes the distance between the embedding jet and the codebook B. And in addition to the codebook and commitment losses from here, they also use the motion reconstruction loss between the decoded motion here and the input ground truth motion for training the VQVA. Then we can obtain the motion token sequences using the pre-trained VQVA encoder from the previous stage. And they also introduced the mask and pad and end tokens for training the transformer with mask motion model. And this model takes text conditions from two parts and generates the text corresponding motions. So they extract sentence level text features from the pre-trained clip model and encapsulate it as a token on the first place of motion token sequences. And it also gets the word level embeddings from the clip models and use them as key end values in the cross-attention layers of a transformer. For mask modeling, they randomly replace the R by L input motion tokens with the mask tokens, where the R is masking ratio following a uniform distribution and L is a sequence length of the tokens. Then they train the text conditions transformer with minimizing the negative low likelihood of the predicted mask tokens here. And in here, Y is original motion token sequences, and YM is the max motion sequence, and W is the text embeddings, which includes the, both the sentence level text and also the word level text. So for the inference, the text to motion generation can be initiated by inputting all mask tokens. Then they, the model predicts the all the tokens and max out the least confidence tokens iteratively. So they chose the mask scheduling function using the decaying function, because at all iterations there is high less confidence. I mean high uncertainty in the prediction. So the model should begin with a large ratio here and only keep a small number of tokens with high prediction confidence. So yeah, and note that in the text in inference time, we cannot know what motion length a model should generate. So the model adopts the pre-trained motion length predictor, which just determines the input motion length corresponding to the text input. 프로그레시브하게 마스크를 진행하는 것이 여기에서 제한된 기시나 이런 쪽에서는 관련 논문을 전에 읽은 적이 없어가지고 여기에서 저는 처음 보긴 했는데 아마 있을 것도 같습니다. 논문에 뭔가 따로 이터러티브하게 디코딩하는 스트레티지에 대해서 사이테이션을 달지는 않았어요. 근데 이터러티브한 뭔가 디코딩 말고 그 패러렐 디코딩, 그러니까 얘는 오토리그레시브 모델이 아니고 패러렐하게 그냥 쫙 넣어서 쫙 뽑는 그런 거는 봤던 것 같아요. 그거는 얘네가 참고로 아마 했을 겁니다. So, the model can do motion editing tasks as well as the text to motion generation by just simply placing the mask tokens into the places where we want to edit. So, for example, to perform the motion in between text, we can just place the mask tokens wherever we want to edit. And for long sequence generation, here, this is just connecting the different motions corresponding to each text and linking the different motions by generating the transition motions. So in here, the model just generates the transition motion tokens conditioned on the previous the end part of the previous motion sequences and the start part of the next motion sequences. And for the upper body editing, they first pre-train the VQA tokenizer, and then they get the motion tokens, and then they concatenate and feed them into the transformer and back out the whole upper part motion tokens to generate the new upper body part motion tokens. So this is the evaluation setup of the paper. They conduct experiments on two standard datasets for text-to-motion generation, which are human ML 3D and KIT ML. And they also followed the evaluation protocol proposed in the previous paper. So they use these 5 metrics for evaluating the generation quality, and for this they use the pre-trained text and motion contrast model, which is from this paper also. And they extract the motion features and the text features from this pre-trained model to calculate the feature distance and whatever. So first, our precision means that for each generated motion, we can get the ground truth text description and the other number of negative text descriptions. And then we calculate the Euclidean distance between the motion features of the generated motions, and also gets the features from the ground text and the other negative text descriptions. And then it is just like retriever text. So top 1 and top 2 and top 3 is just retriever operation. So if the model selects the top 3 samples, if the ground truth text is in the selected pool, they consider it as correct. And MMDIST is multimodal distance, and it computes the average Euclidean distance between the motion features of each generated motion and the text features of each corresponding description in the text text. And FID is just calculating the motion features between the generated motion and the ground truth motion. And diversity measures the variance of generated motions across all the data distributions. And finally, the multimodality represents the average variance of the motion, but it is from single text input. So from the single text input, they generate the multiple motion sequences and compute the Euclidean distance between the generated motion. So this is the quantitative results of the paper. They measures the research on the human ML3D text dataset. And this model outperforms all the diffusion-based models and also the autoregression models on almost all the evaluation metrics. And this model also at least 2 times faster than autoregression motion models, such as GPT and ATT-T2M, and faster than the diffusion-based model, about 2 orders of magnitude. So this is the qualitative research of the model, and the trajectory starts from blue and ends in red. So let's see the result in video. So this is the result of text motion generation, and the input conditional text is a person walks forward and turns completely around and does a cartwheel. So in this case, all the motion tokens are masked before fed into the transformer because it is just generation text. 먹어서 실행이 잘 안 되는데. So the model can generate the motion sequences similar to the front. And this is the another motion editing text. And in this text, the model temporarily impints the mask region of the motion sequences. And in this case, the motion sequences are given. The first 25% and the last 25% of the motion are given. And the model should generate the middle part of the motions conditioned on the text, which is a man through a war. So the MMM can generate the plausible motion sequences compared to the MDM. MDM cannot generate the natural and smooth transition motions. Here. So this is the another motion editing task, and this generates the upper body part when getting the remaining parts of the lower body part. So lower body parts is corresponds to the man rises from the ground, walks in a circle, and sits back down on the ground. And the model should generate the upper body part motion corresponding to the unmanned throws or board. So this is the last applications, and this is the long sequence generation, and this just generates the transition motions between the like different motion sequences, which it corresponds to each text parameters respectively. So the model should link the different motions by generating the transition motions. So red part is the given motions corresponding to the text prompt, and the model generates the blue part, which is the transition motion. So conclusion, the model proposes a novel and simple motion generation and also the editing paradigm, and they use the parallel and iteratively defined decoding for both the high fidelity and fast generation. And they fit for the autoregressive model and diffusion-based models on both the quality and the FPS. And what I wanted to say was that this two-stage approach, which is our response to the BQV and transformer, can be applied to other domains like pitch and phase, and also like other motion domains. So thank you, and please ask if you have any questions.